Hello and good afternoon friends, welcome to CEC live lectures. Dear friends, today in this session we would be discussing in our series on natural products and spectroscopy. In our previous two sessions we have discussed on IR spectroscopy in detail, and today also we would be talking more on IR spectroscopy. And for this very discussion we have once again with us in our studios Dr. Vandana. Dr. Vandana is Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. Dear friends, today in this session you can ask questions from Dr. Vandana live. For that we are communicating with you our toll-free number through which you can ask questions from her. Our toll-free number is 1800-110-430. This is a number through which you can ask question, but you are requested to call us at the last 10 minutes, that is from 4:05 to 4:15, and this is the time where you can call us and we will definitely take your calls and give answers to your questions. So taking the lecture forward, let's welcome our guest Dr. Vandana. Hello ma'am, welcome to the set lecture.
Thank you so much. Hello viewers, we have started a series on natural products and spectroscopy. And in spectroscopy, in previous two lectures, I have discussed in detail about IR spectroscopy. You know what is IR spectroscopy? It is nothing but the interaction of infrared radiations with the organic matter, through which you can identify the particular functional group present in the organic compound. Only IR active molecules can be studied through IR spectroscopy. We have discussed in last two lectures about the alkanes, alkenes and alkynes, and CH stretching, CH asymmetric stretching, symmetric stretching and bending vibrations. We have discussed in detail how can you analyze the alkane, alkene and alkene in the particular organic compounds. Today I am going to discuss more about the rest of the functional group, that is we start with carbonyl compounds. You know what are carbonyl compounds? Nothing but the compounds which contains the carbonyl functional group. And carbonyl functional group present in aldehydes, ketones, acids, ester, amides, acid chlorides and anhydrides. All these kinds of functional compounds contain carbonyl compounds. And this group absorbs strongly in the range of 1850 to 1650. You can see it's a wide range. And because of its large change in dipole moment, we are very much aware of this fact that the compound should have a significant dipole moment to be observed in IR spectroscopy. And you can see this chart shows the range of different carbonyl compounds. You can see anhydride will show approximately at 1810, acid chloride at 1800, anhydride 2 band 1760, ester at 1735 centimeter inverse, aldehyde approximately 1725, ketone 1715, carboxylic acid 1710 and 1690 centimeter inverse amide functional group. So you can see the wide range of IR spectroscopy. We will discuss in detail in coming slides why these functional group particularly absorb these reasons. We can say why these values are higher for anhydride group, why the values are lower in amide group, although all these functional group contains carbonyl compound. The range of values can be explained through the use of electron withdrawing effect, that is inductive effect, resonance effect and hydrogen bonding. An electronegative element may tend to draw in the electrons between the carbon and oxygen atoms through its electron withdrawing effect. We are very much aware of this fact. So carbonyl compounds become somewhat stronger because of the electronegativity difference between carbon and oxygen, and a higher frequency absorption, that is IR absorption, will obtained. Since oxygen is more electronegative, this effect dominates in an ester to raise the carbonyl frequency, because there are two carbonyl groups in ester as compared to ketonic functional group. Resonance may be observed when the unpaired electrons on nitrogen atom conjugate with carbonyl group, resulting in increased single bond character, and is a lowering of carbonyl functional group. This effect is observed in amide. Since oxygen is less electronegative than an oxygen atom, it can more easily accommodate a positive charge, and the resonance structure shown here introduce single bond character into the carbonyl group and thereby lowers the absorption frequency below that of a ketone. We have discussed in the first lecture of IR spectroscopy that how these values changes according to the single bond or double bond. You can see this is the ester RCOOR and this is the amide. You can see electron withdrawing effect raises the carbonyl frequency and resonance effect lowers the carbonyl frequency in case of amide. In acid chloride, that is RCOCl, or the highly electronegative halogen atom strengthens the carbonyl bond through an enhanced inductive effect and shift the frequency to a values even higher than found in esters. So, we have to see the electronegativity factor over here, that is inductive effect. Anhydrides are likewise shifted to frequencies higher than are found in ester. Why it is so? Because of concentration of electronegative oxygen atoms get increase in case of anhydrides because of two carbonyl groups. In addition, anhydrides gives two absorption bands that are due to symmetric and asymmetric stretching vibrations. A carboxylic acid exists in monomeric form only in very dilute solution, and it absorbs at approximately 70-60 centimeter inwards because of the electron withdrawing effect. However, acids in concentrated solution in the free of neat liquid or in solid state tend to dimerize via hydrogen bonding. And you can see over here, this is a one molecule of carboxylic acid monomer RCOOH, and this is the another molecule, and this dotted line indicates the hydrogen bonding between the two carboxylic acid. This dimerization weakens the carbonyl bond and lowers the stretching force constant, resulting in the lowering of carbonyl frequency of saturated acid to about 1710 centimeter inwards. Ketone absorbs at lower frequency than aldehydes. Why it is so? Because of their additional alkyl group. You can see this is the structure of ketonic group, or you can see two R groups or alkyl group or aryl groups are there, and these are, when we are talking about alkyl group, these groups are electron releasing group. So, electron donating and supplies electrons to the carbonyl bond, that is C double bond O. This electron releasing effect weakens the carbonyl bond in ketone and lowers the force constant and the absorption frequency. Now, factors of influencing carbonyl stretching vibrations. First of all, conjugation effect. You can see over here that this carbonyl group, or we can say this conjugation get increased by this double bond carbon, double bond carbon. What is conjugation? Nothing but alternate single and double bond. The introduction of carbon double bond carbon adjacent to a carbonyl group results in delocalization of pi electrons in carbonyl and carbon double bond, or we can say alkene bonds. This conjugation increases the single bond character of the carbonyl group and carbon double bond carbon, and in the resonance hybrid, and hence lowers their force constant, resulting in lowering the frequencies of carbonyl group and double bond absorption. Conjugation with the triple bond leads also this effect. Generally, the introduction of an alpha beta double bond in a carbonyl compound results in 25 to 45 centimeter inverse value lowering of the carbonyl frequency from the base value. That if it is conjugated by alpha beta double bond, the value get increased by this range. A similar lowering occurs when aryl group is introduced. Further, addition of unsaturation at gamma or delta position results in a further shift to lower frequency, but only by about 15 centimeter inverse. So, effect is less over here when we are talking about gamma or delta as compared to alpha or beta conjugation. In addition, carbon double bond carbon absorption shifts from its normal value and about out 1650 to a lower frequency value of 1640 centimeter inverse, and carbon double bond carbon absorption is greatly intensified. Often too closely spaced carbonyl absorption peaks are observed for these conjugated systems and results from two possible conformation, that is cis, S-cis. You can see why we are saying S-cis, because this double bond is cis to this R group, and S-trans, the S-cis conformation absorbs at frequency higher than the S-trans conformation. And in some cases, the carbonyl absorption is broadened rather than split into the doublet. The following examples show the effect of conjugation on carbonyl frequency. Here you can say this is what, nothing but alpha beta unsaturated ketone, and you can see the values. This is aryl substituted aldehyde and this is aryl substituted acid, and you can see the values, how the values varies when the particular groups are attached to carbonyl group, whether we are talking about alpha beta unsaturation or aryl group, or we can say acidic group. Next effect is due to the ring size. For ketones and ester, there is often 30 centimeter inverse increase in the frequency for each carbon removed from the unstrained 6-membered values. For example, you can see this is 5-membered cyclic ketone, and the values get increased by 1750 to 1745. Here also cyclic ketone, 4-member ketone, 1750 to 1780, as the more carbon is released from, or we can say unstrained the ring, or cyclic ester, you can say lactonate also, and the values get increased by 1735 to 1770. This is cyclic amide RCONH, or we can say lactam. The values get increased by from 1690 to 1705 centimeter inverse. In ketones, large rings have frequencies that range from nearly the same values, and in cyclohexanone to a value slightly less than 1715 centimeter inverse. For example, cycloheptanone absorbs at about 1705 centimeter inverse. Next effect after conjugation, and this is alpha substitution effect after ring size. When the carbon next to the carbonyl group is substituted with a chlorine or other halogen atom, the carbonyl band shift to a higher frequency. Why it is so? Nothing but electron withdrawing effects removes electron from the carbonyl carbon. This removes is compensated by a tightening of the pi bond, or we can say shortening of the pi bond between carbon and oxygen, and which increases the force constant, that is K, and leads to an increase in absorption frequency, because these are directly proportional to each other and varies altogether. This effect holds all for carbonyl compounds. In ketones, two bands results from substitution of an adjacent chlorine atom. One arises from conformation in which the chlorine is rotated next to the carbonyl, and other is due to the conformation in which chlorine is away from the group. And here you can say this is the axial position away from the group, and this is equatorial near to this carbonyl group. When the chlorine is next to the carbonyl, non-bonded electrons in the oxygen in carbonyl group are repelled, resulting in a stronger bond and a higher absorption frequency will observed. Information of this kind can be used to establish a structure in rigid ring systems, such as in following examples. We have discussed these two examples. Next step after these three effects is hydrogen bonding effect. Here you can say this is the structure of methyl salicylate, and this dotted line indicates the intramolecular hydrogen bonding. What is intramolecular hydrogen bonding? That is, this electronegative atom of a particular group within a molecule is get attracted or get interacted with the hydrogen atom of the another group. So, this dotted line indicates the hydrogen bonding. When it within the same molecule, it will be intramolecular hydrogen bonding. What it happens here? It lowers the stretching force constant, that is K, and resulting in the lowering of the absorption frequency. Example of this effect are the decrease in the carbonyl frequency of the carboxylic acid dimer and lowering the ester carbonyl frequency in methyl salicylate caused by intramolecular hydrogen bonding. Now aldehydes. Aldehydes show a very strong band for the carbonyl group that appears in the range of 1740 to 1725 for simple aliphatic aldehydes. This band is shifted to lower frequency when it is in conjugation to a carbon double bond carbon, we can say alkene, or with a phenyl group. A very important doublet can be observed in carbon hydrogen stretching region for the aldehyde. What it will be? 2850, 2750 centimeter inverse values. The presence of this doublet allows aldehyde to be distinguished from the other carbonyl containing compounds. Here you can see the IR spectrum of nonenol, and here you can see this is this sp3 or CH stretching. Here you can see the doublet near values of 2850 and 2750. So here you can distinguish from the other carbonyl compounds, that is aldehydic carbonyl compound. IR spectrum of crotonaldehyde, this is the again you can see the doublet because two peaks are there. This is the IR spectrum of benzaldehyde, and here you can see this is the doublet, and other peaks are also there. The spectrum of nonenol exhibit the normal aldehyde stretching frequency. We have confirmed from the spectrum. Since position of these absorptions are not very different from those of ketones, it may not be easily distinguished between aldehydes and ketone. Conjugation of the carbonyl group with an aryl or alpha beta shifts the normal band to a lower frequency. We have discussed this point, and this effect is seen in crotonaldehyde, which has alpha beta unsaturation, in the benzaldehyde, in which aryl group is attached directly to the carbonyl group. Halogenation on the carbon leads to an increased frequency for the carbonyl group. The CH stretching vibrations found in aldehydes for CHO group will be 2750, 2850 are extremely important for distinguish between ketones and aldehydes. Typical ranges for the pairs of carbon hydrogen bands are 2860 to 2800 and 2760 to 2700. The band at 2750 is probably the more useful of the pair because it appears in the region where CH absorption for CH3, for CH2 and so on are absent. The 2850 centimeter inverse band even overlaps with the other carbon hydrogen bands and is not as easy to observe in this spectrum. If the value 2750 spectrum band is present together with the proper carbonyl absorption value, then aldehydic group will be confirmed. The doublet observed is in the range of 2860 to 2700 for an aldehyde is result of Fermi resonance when the stretching or we can say asymmetric stretching vibrations are coupled to each other. The second band appears when the aldehydic carbon hydrogen stretching vibration is coupled with the first overtone of the medium intensity aldehydic carbon hydrogen bending vibration and appearing in the range of 1400 centimeter inverse. The medium intensity absorption is nonenol is at about 1416 is due to the scissoring, that is bending vibrations of the CH2 group next to the carbonyl group. Methylene group often absorb more strongly when they are attached directly to a carbonyl group. Next carbonyl compound is ketones. Ketones show a very strong bond in the range of 1720 to 1708 for simple aliphatic ketones. So we have to remember these range to identify the particular carbonyl compounds. And this band is shifted to lower frequency as we are already studied in case of aldehyde due to conjugation with phenyl group, and due to halogen atom it get increased. The ring strain move the absorption to a higher frequency. So all these three factors we have already discussed, and you can see the IR spectrum of cyclopentanone and IR spectrum of 2,4-pentane dione. Here you can see this is the sp3 CH stretching vibration, and this carbonyl group due to ketonic group will be present at this value, and same over here you can see this is the value of ketonic group approximately to this value. Conjugation effects of carbonyl group with an aryl or an alpha beta double bond shift the normal value to a lower frequency, as predicted in rotational isomers may lead to a splitting or broadening of the carbonyl band. The effect of conjugation on the carbonyl band is seen in mesithyloxide, which has alpha beta unsaturation, and in acetophenone, in which aryl group is attached to a carbonyl group. Both exhibit carbonyl shifts to a lower frequencies, present some typical carbonyl stretching vibration which demonstrate the influence of conjugation. Here you can see different examples. These are the normal and these are the alpha beta unsaturated and these are the enolic beta diketones. And here also you can see the values of IR, that is 1715 for this particular cyclohexanone. This is a journal ketone 1715. Another examples are also here. You can see this is ketene. What is ketene? C double bond C double bond O. And this is the ketonic group with cyclopropane ring. And this is cyclobutanone, cyclopentanone, hexanone, and this is cycloheptanone. So various bands are there you can observe, and you can identify the, because of this values you can identify the particular compound, whether it is ketene or cyclobutanone, cyclopropanone, pentanone, and etc. Cyclic ketones ring strain shift the absorption values to a higher frequency. Ketene is included in the last figure because it is an extreme example of an exo double bond absorption to the carbonyl compound. The S character of the carbonyl group increases as the ring size decreases until it reaches a maximum value that is found in the hybridized carbonyl carbon in ketene. The spectrum of cyclopentanone shows low ring strain increases the frequency of the carbonyl compound. Here are the another examples of ketones, that is alpha diketones. We can also say it 1,2 diketones because the carbonyl group or ketonic group present in 1 and 2 position. Unconjugated diketones that have the two carbonyl groups adjacent to each other show one strong absorption peak at about 1760 centimeter inverse. And if the two carbonyl groups are in conjugation with aromatic rings, the absorption is shifted to a lower value at about 1680 centimeter inverse. And in the later case, in narrowly spaced doublet rather than a single peak may be observed due to symmetric vibrations and asymmetric stretching vibrations. Here you can see the examples with aliphatic and aromatic diketones. Next is beta diketones, that is 1,3 diketones. Beta diketones with carbonyl compound respect to each other may yield a more complicated pattern than those observed for most ketone, that is 2,4 pentane dione. These beta diketones often exhibit tautomerization. You know what is tautomerization? This is, here you can observe, this is a Keto Tautomer because both the carbonyl group is in keto forms. And here you can see this is a keto form and this is enol form. So, enol tautomer, and look at the values, two values are there rather than one, 1723 for symmetric stretching, 1706 for asymmetric stretching, while for here you can see the values for carbonyl compound it will be at value approximately about 1622, and for hydrogen bonding due to OH group with this carbonyl compound you can observe this value 3200 to 2400 centimeter inverse. And these beta diketones often exhibit tautomerization, as we have already said, which yields an equilibrium mixture of enol and keto tautomers. Since many diketones contain large amounts of enol form, you may observe carbonyl peaks for both enol and keto tautomers in case of beta diketones. The carbonyl group in the enol form appearing at about 1622 is substantially shifted and intensified in comparison to normal ketone value, that is 1715 centimeter inverse. And the shift is a result of internal hydrogen bonding, and you can see what is internal hydrogen bonding when there is a hydrogen bonding within the molecule, because this is electronegative atom and this hydrogen atom can have interaction with this electronegative atom of another part. Resonance, however, also contributes to the lowering of the carbonyl frequency to the enol, and this effect includes single bond character. Here you can see this is the, because of this resonance effect, you can see how the resonance took place. Because of this resonance, the bond, double bond becomes single bond, and this effect introduces single bond character into the enol form, subsequently lowering the frequency, that is IR frequency. A weak broad hydrogen bonding or OH stretch is observed for the enol form. At this value we have already said, since the keto form is also present, a doublet for the asymmetric and symmetric stretching frequencies is observed for the two carbonyl groups. The relative intensities of the enol and keto carbonyl absorption depends on the percentages present at equilibrium. The hydrogen bonded carbonyl group in enol forms are often observed in these values, and the keto forms generally appear at the doublet in the range of these values, that is 1730 to 1695 centimeter inverse. Next, keto compounds are alpha haloketones, that is halogen atom present at the alpha carbon atom with respect to this ketonic group. Substitution of a halogen atom on the carbon shifts the carbonyl absorption peak to a higher frequency. We have discussed in detail in the last slides why it is so. Similar shifts occur with the other electron withdrawing groups such as alkoxy group. For example, the carbonyl group in chloroacetone appears at this value, whereas in the methoxyacetone appears at this value. You can see the higher frequency observed in case of methoxyacetone. When the more electronegative fluorine atom alpha is at position alpha is attached, the frequency shifts to even higher values because the high electronegativity of fluorine atom, and the value will be 1781, 17 inverse. Now, binding modes. A medium to strong absorption occurs in the range from 1300 to 1100 centimeter inverse for coupled stretching bending vibrations in the carbon-carbonyl carbon group of ketones. Aliphatic ketone absorbs to the right in this range as seen in the spectrum of 3-methyl-2-butanone, where a band appears at about approximately 1180 centimeter inverse. Aromatic ketones absorbs to the left in this range as seen in the spectrum of acetophenone, where a band appears at about 1260 centimeter inverse. A medium intensity band appears for methyl group adjacent to a carbonyl group at about 1370 centimeter inverse. For symmetric vibration, these methyl groups absorb with greater intensity than the methyl group found in hydrocarbons. Now, carboxylic acid. You know what are carboxylic acid? Nothing but RCOOH. So, here you can see it is a combined functional group because of carbonyl group and because of hydroxyl group. So, we will get both intensity band, both IR stretching vibrations or bending vibrations in the spectrum. Let us discuss in the detail of carboxylic acids. Carboxylic acids show a very strong bond for carbonyl group that appears in the range of 1730 to 1700 for simple aliphatic carboxylic acids. In the dimeric form, we have already discussed that carboxylic acids in concentrated form exist in dimeric form, and in dilution it exists as a monomeric form, which normally does not observed in experimentally. This band is shifted to lower frequencies with the conjugation to a carbon double bond carbon or due to phenyl group. And the OH stretching appears in the spectrum as a very broad band from value 3400 to 2400 centimeter inverse. This broad band centers on about 3000 centimeter inverse and partially obscures the carbon stretching bands. If this very broad hydrogen bonding stretching vibrations is seen along with the carbonyl group, it almost certainly indicates that carboxylic group is there in the given organic compound. Let us see this spectrum of IR spectrum of isobutyric acid, here you can see this is a broad spectrum due to oxygen hydrogen stretching vibrations, and this is the peak which shows the due to the carbonyl stretching. So, OH stretching usually we have already stated a broad band in the range of this 3400 to 2400 centimeter inverse, and you can see this, you can note this also that it often overlaps with the carbon hydrogen absorptions, and the carbonyl stretching broad occurs at due to carbonyl group 1730 to 1700 centimeter inverse. And we are very much aware of this fact that conjugation due to aryl group or due to benzene group, or we can say phenyl group, or due to alkene groups moves the absorption band to a lower frequencies. Carbon single bond oxygen stretching occurs in the range of 1320 centimeter inverse to the range of 1210 centimeter inverse. Here this is the IR spectrum of benzoic acid, and you can see this is the, you can see this is OH stretching due to hydrogen hydroxyl group of carboxylic acid, this is benzoic acid, and here you can see this is the carbonyl peak, a very sharp peak will observed in case of benzoic acid, or we can say when carboxylic group is there, that is carbonyl peak should be there, a prominent peak should be there along with a prominent peak, broad prominent peak due to this hydroxyl group must be there, in addition to this aromatic carbon double bond carbon peak. Then only we can say it is the spectrum of, or we can more precisely say this will be the IR spectrum of benzoic acid. The most characteristic feature in the spectrum of carboxylic acid is extremely OH absorption occurring in the range of this, we have already discussed, and this band is attributed to the strong hydrogen bonding present in the dimer. The absorption often obscures the CH stretching vibration we have seen in the figure, and if this broad hydrogen bonded band is present together with proper carbonyl absorption value, for sure carboxylic group will be there. The carbonyl stretching absorption which occurs at about 1730 to 1700 for the dimer is usually broader and more intense than present in the aldehyde or ketonic group, then only we can say this is a carboxylic group. For most acid, when the acid is diluted with a solvent, the carbonyl absorption appears between 1760 to 1730 centimeter inverse for the monomer. However, monomer is not often seen experimentally. It should noted that some acid exists at dimer even at high dilution. Conjugation with a carbon double bond carbon or aryl group or phenyl group usually shifts the absorption band to a lower frequency as shown in the previous spectrum of benzoic acid, and halogenation will lead to the increase in frequency due to an alpha carbon atom. The carbon single bond oxygen stretching vibration for acids appears near 1216 due to dimer as a medium intensity band. A broad band attributed to hydrogen bond in OH out of plane bending vibration appears at about 930 centimeter inverse value, and this latter band is usually of low to medium intensity. The next carbonyl functional group is esters. Esters show a very strong peak at about in the range of 1750 to 1735 for simple aliphatic esters. And as we have discussed earlier also, when this carbonyl band of ester group is shifted to a lower frequency because of conjugation. On the other hand, conjugation of carbon double bond carbon or phenyl group with a single bond oxygen atom of an ester leads to an increased frequency. The ring strain moves the carbonyl absorption to a higher frequency in cyclic esters, that is in lactones. Here you can see the IR spectrum of ethyl butyrate, and this is the structure of ethyl butyrate. These are the values, the prominent peaks you can see over here. This is the very sharp peak due to carbonyl stretching vibrations, and this is the another peak due to this sp3ch stretching vibrations. So, we have discussed many carbonyl compounds till now. We have discussed the prominent peak of carboxylic acids, we have discussed about the aldehydic group, we have discussed about the ketonic group. So, hope you understand, and these values will help you to identify the given functional group in the organic compound. Thank you so much. Hello viewers, let us discuss more about the IR spectroscopy part 3rd. We are discussing about the carbonyl compounds, and in this slide we are discussing about the esters. You know what is ester? It is nothing but RCOOR, that is carbonyl group there, and along with carbonyl group there is another electronegative atom, that is oxygen is there. That is why the carbonyl band is shifted to a lower frequency when it is conjugated with carbon double bond carbon or phenyl group, and conjugation with carbon double bond carbon or phenyl group with the single bond oxygen of an ester leads to an increased frequency, because oxygen is electronegative atom, and ring strain moves the carbonyl absorption to a higher frequency in cyclic esters. This is the IR spectrum of ethyl butyrate, and you can see the prominent peaks due to this carbon hydrogen stretching due to this carbonyl group of this carbonyl group, and this is carbon oxygen single bond. These peaks are here, you can see. The more IR spectrum of methyl, methacrylate, IR spectrum of vinyl acetate. Let us discuss first this methyl methacrylate. Here you can see this is the peak, prominent peak, sharp peak due to carbon hydrogen stretching. This is carbon oxygen in conjugation with this carbon double bond carbon. Two peaks are here. This is due to the carbonyl group. This is due to the carbon double bond carbon. You can see this is an intense peak when this is the intense peak and this is the medium peak. And these peaks are due to the carbon oxygen stretching. And this is the IR spectrum of vinyl acetate. Here you can see this peak is not very prominent, but peak is there. An intense peak is there. And this is the carbonyl group, and this is the carbon double bond carbon peak, and this is carbon oxygen stretching peak, and this is vinyl peaks. This is the IR spectrum of methyl benzoate. Here you can see this is the methyl benzoate. So, first of all we have to look this carbonyl group peak, and you can see this is the carbonyl group. Now, carbon double bond carbon because of this phenyl group. Here you can see this is the doublet, and CH3, sp3 because of CH stretching, and sp2 because of this sp2. You know, in phenyl group every carbon is sp2 hybridized, so sp2 CH stretching must also be there, and these peaks are due to this carbon oxygen single bond. So, we can observe this is the IR spectrum of methyl salicylate. Here you can see this is intramolecular hydrogen bonding. So, we have to look for OH peak due to this OH. This is, you can see the broad spectrum, and this peak is due to the sp3ch stretching vibrations. This peak is due to the carbonyl group. This is the carbonyl group, and these peaks are due to the carbon double bond carbon because of this aromatic compound. So, you can easily analyze or you can identify the particular kind of functional group in the organic compound. Conjugation with carbonyl group, or we can say alpha beta unsaturation or aryl substitution. Carbonyl stretching vibrations are shifted by 15 to 25 values to a lower frequencies when it is in conjugation with alpha beta unsaturation or aryl substitution. The spectra of both methyl methacrylate and methyl benzoate show the carbonyl absorption shifts from position in a normal ester ethyl butyrate. Also notice that carbon double bond carbon absorption band at 1630 in methyl methacrylate has been intensified over what is obtained with a non-conjugated double bond. These are the three different esters you can see. This is ethyl butyrate, this is methyl methacrylate, that is alpha beta unsaturation is there within conjugation with the carbonyl group, and here you can see a methyl group is there. Sorry, a phenyl group is there in the conjugation with this methoxy group. So, you can see the values differ from 1738 to 1725 to 1724. Conjugation with ester single bonded oxygen atom. Conjugation involving the single bonded oxygen shift the carbon oxygen vibrations to a higher frequencies. Because of this carbon oxygen bond, apparently the conjugation interferes with the possible resonance with the carbonyl group and leading to an increase in the absorption frequency of the carbonyl bond. Here you can see what kind of resonance is there. Because of this, lone pair of electron get delocalized over this area, over these two carbon atoms. In the spectrum of vinyl acetate, the carbonyl band appeared at 1762 centimeter inverse, an increase of 25 centimeters above a normal ester. Notice that carbon double bond carbon absorption intensities get increased in a manner similar to that pattern obtained with the vinyl ethers. The substitution of an aryl group on oxygen atom would exhibit similar pattern. Here you can see how the values varies for ethyl butyrate, for phenyl acetate, for phenyl acetate. Next effect is hydrogen bonding effects. When intramolecular hydrogen bonding is present, the carbonyl is shifted to a lower frequency. Here you can see this is the intramolecular hydrogen bonding and the value is at about 1680. Cyclic esters, or we can say lactones in common, the carbonyl vibrations get shifted to higher frequencies with the decreasing ring size. So, as the ring size decreases, the value get in higher position. The unstrained 6-membered cyclic ester, that is 5-valeroactone, absorbs at about the same value as a non-cyclic ester, that is 1735 centimeter inverse. Because of increased angle strain, the gamma butyrolactone absorbs at about 35 centimeter inverse higher than the delta valerolactone. So, you can observe at what value will be given. So, these are the examples you can see, these are the normal values and these are the different values. How the values get decreased due to conjugation. You can see this carbonyl group is in conjugation with this carbon double bond carbon, and here you can see this carbonyl group is in conjugation with phenyl group. So, whether this kind of conjugation is there due to carbon double bond carbon or alkene, or here you can see with phenyl group the value get decreases, and here you can see the values get increased due to alpha beta or aryl conjugation. Another examples, here you can see this is lactone, or we can say cyclic ester RCOOR. This is delta valerolactone and this is gamma butyrolactone. Alpha halo effects. Halogenation on the carbon alpha carbon leads to an increase in the carbonyl frequency. Alpha keto esters, in principle one should say 2 carbonyl groups for a compound with a ketonic and ester functional group. Usually one CA shoulder on the main absorption band near 1735 centimeter inverse or a single broadened absorption band. Beta keto esters. Here you can see this is the ester R COOR, but in this R, alpha beta, you can see this carbon will be alpha with respect to this esteric carbonyl carbon, and this will be beta. Another thing you can see over here, tautomerization. These are two carbonyl groups. This is called Keto Tautomer, and this is the enol form because OH is there. Hydroxyl group, or we can say enol group is there. Although this class of compounds exhibit tautomerization, we have explained over here, like other observed in beta diketones we have discussed in earlier slide, less evidence exists for enol form, that is this particular form, because alpha keto esters do not enolize to a great extent. Beta keto esters exhibit a strong intensity doublet for the two carbonyl groups at about 1720 centimeter inverse and 1740 centimeter inverse in the keto tautomer for ketone and ester groups. Evidence for weak intensity carbonyl band in the enol tautomer appears, often observed as a doublet, that is a peak get splits into two peaks, appears at about 1650-70 inverse. Because of the low concentration of enol tautomer, one generally cannot observe the broad OH stretching that should be observed in case of beta diketones. Here you can say the different lactones. This is 4-membered, 5-membered and 6-membered. And you can say the ring size effect, as the ring size get increases, the value get decreases, or we can say ring strain get released from 4 to 6. This is nothing but alpha beta conjugation with this esteric carbonyl carbon. How the values get changed? You can see for 5-membered ring it will be approximately at about 1750 centimeter inverse. For 6-membered lactones with in alpha beta conjugation, the values approximately 1725. Conjugation with oxygen. Here you can see this is 6-membered ring and this is 5-membered ring. So, we can detect all these particular lactones in IR spectrum when we see these values. Carbon oxygen single bond, here you can see single bond stretching we are talking about in esters. 2 or more bands appear in the range from 1300 to 1000 centimeter inverse. Generally, the carbon oxygen stretching next to the carbonyl group of the ester is one of the strongest and broadest band in the spectrum. So, you can easily analyze the ester in a particular organic compound. This absorption appears between 1300 and 1150 centimeter inverse for most common esters, that is esters of aromatic acids absorbs nearer the higher frequency and of this range, and esters of saturated acids absorb nearer the lower frequencies. The carbon oxygen stretching for the alcohol part of the ester may appear as a weaker band in the range from 1150 to 1000 centimeter inverse. In analyzing the 1300 to 1000 centimeter inverse region to confirm an ester function group, it is usually sufficient to find at least one very strong and broad absorption to identify the ester group, that is in this particular range 1300 to 1000 centimeter inverse. Next function group of carbonyl compound is nothing but amides. You know what is amide? RCONH2. So, one carbonyl group is there and amine are also is there. Amides show very strong peat due to this carbonyl group in the range of 1680 to 1630 centimeter inverse. And NH N single bond H stretching will observed in the range of 3475 to 3150 centimeter inverse. Unsubstituted primary amides RCONH2 show 2 bands in the region, while monosubstituted amides and RCONHR show only 1 band. So, you can easily distinguish between these amides. The presence of NH bands plus an unusually low value for carbonyl would suggest the presence of an amide functional group. Disubstituted, that is tertiary amide. What will be tertiary amide? Nothing but when 2 hydrogen atom of NH2 group get substituted by 2R group, it will be your tertiary amides. So, that will show carbonyl in the range of 1680 to 1630 plus it will not show any NH stretching because no NH bond is there. So, you can easily distinguish from the other amides from primary from secondary. These are the recap and this is the IR spectrum of propionamide. Here you can see this is the doublet due to NH2 stretching. Here you can see the prominent peak due to carbonyl stretching, and moreover what is written over here you can see this peak get overlapped with NH band. That is because of this NH band this peak get broadened, it is not sharp anymore. This is the IR spectrum of N-methyl acetamide. These are the values you can easily observe. This broad peak is due to the NH, because of this NH, this is the overtone, and this peak is due to the CH stretching. Here you can see 2 methyl groups are there, and this is the prominent peak because of this carbonyl group, and another bond is there, another peak is there due to this NH band. Now, NH stretching vibrations and CN stretching bands. A pair of fairly strong NH stretching bands we have seen in last spectrum at about 3350 and 3180 for primary amide in a solid state. The peak due to 3350 and 3180 bands from asymmetric and symmetric vibrations respectively. Here you can see that asymmetric stretching vibrations occurs at higher value. It is generally occurs in IR spectrum of functional group of different functional groups. In the solid state, secondary amides and lactams. What are lactams? Nothing but cyclic amide give 1 band at about 3300 centimeter inverse. A weak band may appear at about 3100 centimeter inverse in secondary amides, and it is attributed to a Fermi resonance and overtone of the 1550. A CN stretching band appears at about 1400 centimeter inverse for primary amides. Now, NH bending bands. In the solid state, primary amides give strong bending vibrations. Generally, bending vibrations are not strong, but here you can say these are strong bending vibrations are there in the range of 1640 to 1620 centimeter inverse. They often nearly overlap with the carbonyl stretching bands due to the CO bond, C double bond O bond. Primary amides give other bending bands at about 1125 and a very broad band in the range from 750 to 600 centimeter inverse. Secondary amides give relatively strong bending bands at about 1550 centimeter inverse, and these are attributed to a combination of CN, carbon single bond nitrogen stretching band and a nitrogen single bond hydrogen bending bands. The next carbonyl compound is acid chloride. It is nothing but RCOCl, that is a carbonyl group is there and a electronegative atom chloride is there. So, what happens? This acid chlorides will appear in the IR spectrum in the range of 1810 to 1775 centimeter inwards for aliphatic chloride. Acid chlorides and anhydrides are the most common functional group that have a carbonyl appearing at such a higher frequencies. And conjugation lowers the frequencies. You know how it lowers the frequency because of the weakening of the bond, that is carbon double bond oxygen. Carbon double bond oxygen stretching occurs in the range of 1810 to 1775 in the unconjugated chlorides, and conjugation lowers the frequency we have discussed, and the band due to carbon and chlorine halogen atom stretching vibrations occurs in the range of 730 to 550. So, you can easily analyze acid chlorides because of the higher values of carbonyl compounds as well as a peak due to this carbon chloride in the range of 730 to 550 centimeter inwards. Here you can see the values. You can see this peak is very prominent because of this intense peak. However, it is a broad peak, and here you can see this peak is due to this carbonyl group. So, acid chloride can easily analyze or identify in IR spectrum because of these two values, higher values because of carbonyl compounds as well as carbon single bond chloride stretching vibrations. This is the example, that is IR spectrum of benzoyl chloride. What is the structure of benzoyl chloride? You can see this is C6H5 phenyl group is in conjugation with this carbonyl compound, and we have already stated that conjugation lowers the frequency, and because of this conjugation, or we can say resonance, this value get decreased, and here you can say however this carbonyl group must be in higher position in case of acid chloride or anhydride, this value get decreased. And these are the another peaks due to Fermi resonance, carbon double bond carbon. This peak is due to this carbon and aryl group, and this peak is due to this carbon, carbonyl carbon and chloride group. Hence, we have discussed many functional groups. We have discussed aldehydes in details, we have discussed ketones in details, we have discussed esters and carboxylic acid. So, while elucidating this structure IR spectrum of any organic compound, you must have an idea that on particular value which carbonyl group is there, because number of carbonyl compounds are there. So, you have to look minutely that particular compound carbonyl group is there along with the another effect. Hope you understood this lecture.
With this note, thank you ma'am, thank you so very much, and dear friends, if you have any queries or if you want to give your feedback for the particular lecture, then do write to us at info.cec@nic.in. We would be meeting again soon. Till then, take care, goodbye. Thank you ma'am, thank you
so much.